Hi everyone, this is Kruti Jaipancholi, Assistant Professor in LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject Analog and Digital Communication System. From this video, you will learn about Phase Lock Loop, PLL. This is the last topic of the unit, amplitude modulation and demodulation. What is a phase lock loop? It is the very important device that is used for tracking the phase and frequency of the carrier component of an incoming signal. It is also used for synchronous demodulation of AM signals with suppressed carrier or with a little carrier, that's a pilot carrier. It is also used in case of the analog and digital component. It can be also used for the detection of the angle modulated signals, especially under the condition of the low signal to noise ratio. The angle modulated signals, in that the frequency modulation and the phase modulation that we will discuss in the next unit. Signal to noise ratio. Signal to noise ratio, where the noise is less, the signal to noise ratio that's higher, and we are always demanding for that kind of the situation. If this noise is high, then the signal to noise ratio that is the less, and especially under that kind of the conditions where the low signal to noise ratios are there, this can be used. The applications in a number of clock recovery system, including timing recovery in the digital receivers, and that is why we can say that a PLL that plays a key role in nearly even modern digital and analog communication system. PLL has three basic components that are: one is voltage control oscillator. It is the VCO. According to the applied voltage, the frequency that can be changed produced by the VCO. Multiplier, serving as a phase detector or a phase comparator, and a loop filter HS. It works as a low pass filter. So three basic components are required in case of the phase lock loop: voltage control oscillator, multiplier, and the loop filter. Using all these three basic components, we can draw the block diagram and the equivalent circuitry for the PLL. PLL and its equivalent circuit. Here you can see the block diagram of the PLL circuit, which consists of three basic components: loop filter, voltage control oscillator, and multiplier. The input signal, it is the A sine omega CT plus theta IT, which is multiplied with the frequency produced by the voltage control oscillator. It's a 2B sine 2B cos omega CT plus theta 0 T. Loop filter will pass it's a low pass filter. Okay, so output produced by this, it's a E0 T. It is the equivalent circuit for the PLL, which consists of the three basic components that are the low pass filter, voltage control oscillator, and the multiplier. So by using that, we can have the input signal having the phase theta IT, okay, theta IT, then the feedback that is the voltage control oscillator having the phase, it's a theta 0t. By using this theta it and theta 0t, the signal it is generated, it is the theta et. Here we have the component which is the low pass filter, okay. It will pass the low frequency component, it will attenuate the high frequency component, it will suppress the high frequency component. So we know that high frequency component over here is what? It's a carrier signal. So you can have the only the component, it is the sine theta e of t, and the output will be generated. This is the impulse response of the low pass filter, and output will be generated. It is the theta 0 is equal to C E0t, where C, okay, that are the constant. So the operation of the PLL, it is similar to the feedback system which you learned earlier. So a typical feedback system, the feedback signal tends to follow the input signal. Always the feedback signal that is trying to follow the input signal. Now if the feedback signal and the input signal both are same, the difference will be generated would be 0. In that we can say that there is no error. But if you are applying the some input signal, if you have a feedback signal, and if the feedback signal and the input signal both are not same, some error signal will be generated, okay. And always the feedback signal that is trying to reach the input signal. So that is actually the goal of this kind of the system. So a PLL that works on the principle, except that the quantity feedback and compared is not the amplitude but the phase. This kind of the question can be asked in the exam also, that in the PLL, as you know that it is the part of the amplitude modulation, but over here the parameter which would be compared, it's not the amplitude, it's always the phase. So we have to keep in mind that PLL works on the principle that except that the quantity feedback and compared, that's not the amplitude but it's always the phase. So VCO adjusts its own frequency such that its a frequency and the phase can track the input signal, and at this point two signals are in synchronism. So if the two signals are in synchronism, okay, then and then we can track the frequency and the phase. If they both are not synchronized, we don't have the idea about the phase change, okay, or the where the frequency would change or where the phase would be changed. So suppose the VCO is controlled by the, as I said earlier, VCO is controlled by the input voltage. Now if a input voltage from to the VCO, okay, the frequency that can be E0t, and its output is a sinusoidal with the instantaneous frequency, and which can be given by omega t is equal to omega c plus c E0t, where c is the constant of the VCO and omega ct is the free running frequency when E0t is equal to 0, where when the E0t would be 0, the E0t would be 0 only when the input signal and the feedback signal both are same. So E0t would be 0. So that is only the ideal case, while this two component will be same. In the practical situations it would be happen, okay, by adjusting the loop filter response, by adjusting the voltage control oscillator frequency. So the multiplier output is low pass filtered by the loop filter and then applied to the VCO. The voltage changes the frequency of the oscillator and keeps the loop locked by forcing the VCO output to track the phase of the input sinusoid. So the VCO output is B cos omega Ct plus theta 0 t, and the instantaneous frequency is omega c plus theta 0 t. So theta 0 t is equal to Ce 0 t, where C and B are the constant parameter of the PLL. Now we'll do some further analysis of this kind of the VLL. Let the incoming signal is A sin omega Ct plus theta it. If there is some phase change, then this equation that would be A sin omega 0 t plus psi t. But if it is not happen, then I can go for my incoming signal is A sin omega Ct plus theta it, where theta it is equal to omega 0 minus omega Ct plus psi t. This input signal applied to the multiplier, and multiplier having the two response. One is from the input signal and another one that is from the VCO. So the multiplier output is AB sin omega Ct plus theta I cos omega Ct plus theta 0. So by applying the formula, trigonometric formula, okay, by applying the formula, not trigonometric, it is the 2 sin cos, so it is equal to the AB by 2 sin theta I minus theta 0 plus sin 2 omega Ct plus theta I plus theta 0. Now we have the output, okay, of that multiplier you have seen. It is given to the low pass filter. What the low pass filter will do? The low pass filter will suppress the high frequency component. So from that two component, the low frequency component will be passed through the low pass filter, but the high frequency component is suppressed. Therefore, the effective input to the loop filter is 1/2 AB sin theta it minus theta 0 t. Now if the HT, that's a unit impulse response of the loop filter, then E0 t is equal to HT convolved with the component, low frequency component, it's a 1/2 AB sin theta it minus theta 0 t. This component we are putting over here. So E0 t is equal to HT convolved with the 1/2 AB sin theta it minus theta 0 t. So that is equal to 1/2 AB integration 0 to t HT minus x sin theta ix minus theta 0x dx. So now the theta 0 t is equal to a, okay, and we are putting the value for the this k, okay, it is the 1/2 cb, and by putting that value, the theta 0 t is equal to ak is integration 0 to t ht minus x sin theta ex dx. So theta et, okay, that is the phase error, it is equal to theta it minus theta 0 t, okay. So this is the equation for the loop filter, and in that we have taken the block diagram, and for that block diagram the PLL design, okay, the equation is this. So we can also say that here the loop filter that we are designing, we are taking, having the response is the HS and the gain is the AK. A different loop filter that enables the PLL to capture and track the input signal with the different types of frequency variation. So the loop gain that also affect the range of the trackable frequency variation, as well as we can say that the such kind of the PLL that can be helpful for such kind of the detection of the phase and the frequency. Okay, so we will also do the other kind of the analysis, that is the small error PLL analysis, as well as the Costas phase lock loop system, as well as the first order PLL loop analysis in the next video. So thank you very much everyone.